Welcome back for video number 2 in the Related Rates series. And today we're going to first talk about a process that I'd like you to try to follow. I can't force you to follow it, but I think that if you follow a process, you're more than likely going to get the problems right. We're going to be moving away from just functional values and moving into some word problems, so we're going to have to go through some identification of particular things in our problem that we want or need to be able to solve it. So there's a structure for approaching related rate problems, and this is what it is. It's a 3-step process, and I will write down each word and then talk about them. And there'll be a little kind of acronym that we'll use as we go along. And the first is, the word equation. All right, so with equation, the question really that you're being asked is, what equation do you know or are you given, because sometimes you're going to be given an equation, that relates the variables in the problem. So you may have to identify something in your mathematical subconscious, or there may be just a formula on a piece of paper that's given to you that's like, hey, do you remember 1/3 pi r squared h is the volume of a cone? So we need to identify an equation. So that's part 1. Part 2 is, are we given any rates? Given rate. With given rate, the question that you're trying to answer is, do you know how something is changing in the situation? So related rates, we're going to be looking for how things are changing. So what do you know, or what are you trying to find, both of which could be considered rates. And if you know what those are, write them in terms of the variable. So make sure that you write them as dr dt, dx dt, dy dt. Don't write them in words. Write them in terms of the variable that you are going to be using. And finally, the last one is, what are you finding? So obviously, this is going to be a big one, because if you don't know what you're finding, you won't know when you've figured out the answer to the problem. All right, so the final piece of the puzzle here is write down a variable or rate that you are looking for. So write it down as the variable or the rate. So are you looking for x, or are you looking for dx dt? You'll know that you're doing the problem right if you're able to solve for your missing variable. If you don't have a missing variable that you can solve for, you're not going to be able to figure that out. So those are the things. I like to kind of have a little acronym here of EGF. I say eat good food, because that's what everyone should do. Eat good food. For equation, given, and find. So if you remember eat good food, that'll remember the 3 things that you're supposed to go through. And I'll try to model that on the next couple of problems. All right, the next few problems we're going to take a look at are pretty classic related rate problems. So anyone who takes calculus is essentially doing these problems. The first is the penny concentric circle problem. Pebble concentric circle problem. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So I think you've all seen this before, or at least a picture of it, right? This, from the center, these ripples kind of radiate out. They're circular, so they're concentric circles. The radius r of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So another thing that's not part of what I asked you to do is, sometimes it's also good to kind of label some things. So I know that I'm dealing with a radius of 4 feet here, and I'm trying to find the rate of change of the area, the rate at which the area is changing when the radius is 4, and I know a constant rate of 1 foot per second for the radius. So trying to find how the area changes. So the equation that relates these things is A is equal to pi r squared, the area of a circle. I am given a rate. I am given the fact that the radius is increasing at a rate of 1 foot per second. So I know that dr dt is equal to 1. and I am trying to find dA dt. I'm trying to find the rate of change of the area, so dA dt, specifically when r is equal to 4. So as I look back at my equation that relates my variables, I only have two variables. I have a and r. I know dr dt, and I'm looking for dA dt. And I do know that when I take the derivative of r squared, I'm going to be left with a variable r. So it's going to be imperative that I also know that r equals 4 will be substituted in. Should allow me to solve for dA dt. So here we go. Finding my related rates equation, I get that dA dt is equal to 2 pi r dr dt. I'm looking for dA dt, so dA dt, that's awesome that that's in the problem, is 2 pi r is equal to 4, and dr dt is equal to 1. So dA dt is equal to 8 pi. Now, I do know some units here. This is, the radius was changing at 1 foot per second, so my area is going to be changing at 8 pi square feet per second. So that is my value of dA dt. My related rates equation solved for dA dt with my given information. Alright, I went ahead and jumped ahead and filled some of this in so that we can save some YouTube time. But in example 5, you have a spherical balloon. So my volume equation is going to be 4/3 pi r cubed. That's the volume of a sphere. And air is being pumped in at a rate of 4.5 cubic feet per minute. So again, that's kind of a giveaway right there, cubic feet per minute. So that's a rate of change of volume, because cubic feet is volume change. So 4.5 cubic feet per minute. Find the rate of change of the radius, so find dr dt when the radius is equal to 2. Alright, so I have all of that listed. Time for us to go to our related rates equation. So dV dt is equal to 4/3 pi r cubed. I want the derivative of that. When I take that 3 and bring it down when using the power rule, it's going to cancel out the 3 in the 4/3. So I'm going to have 4 pi r squared dr dt. And I am trying to find dr dt, so I know that dr dt then can be found by taking dV dt divided by 4 pi r squared. I am given that dV dt is 4.5, 4 pi constant, r squared, while r is equal to 2, so r squared is 4. So that would be 4.5 over 16 pi. 4.5 over 16 pi as my dr dt. Specifically, this is going to be in feet per minute, because dr dt would, r is measured in feet, and then the rate of change is per minute, so 4.5 over 16 pi feet per minute is my dr dt value. Okay, I apologize for the last example. For some reason the picture didn't make it into my PowerPoint for this, so I'm going to have to just go with the rudimentary drawing as it's given over here. But this is the airplane example. You're flying at a height of 6 miles, so you'll notice that I've labeled my picture over here. There's a height of 6 miles, and you're flying over a radar station as shown in the picture. So the radar station's over here in your picture. And it says if S is decreasing at a rate of 400 miles per hour when S is equal to 10 miles, what is the speed of the plane? So in the picture, S is given as the hypotenuse of this triangle. And the question is, what is the speed of the plane? Well, if you notice, this problem ends up generating a right triangle. I have a height of a triangle of 6. I have this hypotenuse of S, which is set at 10. I know some information about the rate of change of S, so I know dSdt, and I want to know how fast is the plane flying. Well, in our class, whenever we talk about the speed of the plane, we were just talking about horizontal speed. So horizontal speed is going to be measured as dx dt. So I want to find dx dt. So I got to get a few things down here. The first is the equation that relates the values in my triangle. Well, no, this is a triangle. It's a right triangle. There's a couple of triangle formulas. There's an area formula. There's a formula that relates the angles to the sides, but most specifically I'm dealing with s ds dt, x dx dt. And those are just the lengths and the rates of change of the sides of my triangle. So I'm just going to generically say a squared plus b squared equals c squared. I'm going to be using the Pythagorean theorem to deal with my particular triangle. I know that I am given a few things. I am given ds dt, and I am given that ds dt is decreasing at a rate of 400 miles per hour. So ds dt is actually negative 400. It has to be negative because it's decreasing. And I know that s is equal to 10 in my problem. I want to find the speed of the plane, which we just discussed is going to be dx dt. So here's what I'm given. Now this one's going to require just a little bit more work. So there are things that are changing in the problem like ds dt and dx dt, but there are other things that are constant, like 6. 6 never changes. 6 is constant. If I were to take the derivative of the height of the plane, it would be dh dt would be 0 because the plane is not going up or down. It's just flying in a perfectly horizontal manner. In this particular problem, I am also told that I am looking at for when s is equal to 10. And so if I were to take a picture at that time, the triangle would have lengths of 10 for its hypotenuse and 6 for its vertical side. I could find the value of x by using the Pythagorean theorem. I would know that x squared plus 6 squared would have to equal 10 squared. So that would be x squared plus 36 equals 100. X squared would equal 64. So x would equal plus or minus 8, but I am only dealing with the value that is positive because x has to be positive. So I do know that my x value is 8. So if I take and rewrite my equation up top with the things that I do know, I know that when s is equal to 10, x is equal to 8, and that the y component is 6. Now, the only thing that doesn't change, though, as this plane is flying, is the 6. So before substituting any of those values in, I need to generate my related rates equation. So the related rates equation that I am going to write down here is that x squared plus 6 squared is equal to s squared. Again, I don't want to plug in those constant values because they're technically not constant as the plane is moving. So my related rates equation would then be 2x dx dt. The 6 squared just becomes a 0 when taking a derivative of, and then that gives me 2s ds dt. I can cancel the 2's out of each side, and I get x dx dt equals s ds dt. And I am going to be looking for dx dt. So dx dt is equal to s ds dt divided by x. When substituting those values in, s is equal to 10, ds dt is negative 400, and x is equal to 8. So I get negative 400, negative 4,000 divided by 8, which is negative 500 miles per hour. Now the question is, what is the speed? X is decreasing as the plane is moving this way. X is getting smaller and smaller and smaller and smaller. So dx dt has to be negative, but the question is, what's the speed of the plane? And as we know, speed is a magnitude that we take the absolute value to find. So our speed is actually equal to positive 500 miles per hour. And that is example number 6. All right, so that's going to do it for today's lesson. We'll pick up with example number 7 in the next set of videos.